and be happy to be here in that time and also to stay on. So thank you again for the organizer. So I will speak about, so in fact, my lecture. So the aim will be to speak about the following theorem, which is kind of a combo between work of Domani, Girardel, and Osin, and something I did during my gym. So these are two different work, but and say that for any field, the Cremona group is acylindrically hyperbolic. So I will see this will mean that in fact okay, well, it will be one of the reasons why the Cremona group is a unique group. And also I wanted to comment that so the Cremona group is I will explain what it is. It's a group coming from algebraic geometry. It's not a finitely generated group, so usually, well, we don't like this so much in geometric group theory. But nevertheless, using tools from geometric group theory, it has been really very fundamental to study this group. And this is okay. My aim is to convince about this to convince you about this during these three lectures. So today, my aim will be to speak about to introduce you the Cremona group and the notion of acylindrically hyperbolicity. And in the second talk, I will explain you the action of the Cremona group on a nice hyperbolic space, well, an hyperbolic space. And the third part will be to explain you how this proof works. So if you have any questions, please. So I will first start with the notion of acylindrically hyperbolicity. So acylindrical. So okay, maybe we would have been better to start with the Cremona group, but I wanted to be sure to have introduce the material for the exercise. So I start with it. So in this part, we will consider a group acting on a metric space. So okay, all my action will be by isometries. So I stated here, but then I will not speak about it anymore. And this will be always a metric and geodesic space. And also, I want for what we include that this space is hyperbolic. So, okay, I don't know if I should define it. If someone, okay, Sebastian speak about it already before, but maybe I can say fast. So, being not hyperbolic means that there exists a uniform constant such that all triangles are delta thin, meaning that if you take 3 points and 3 geodesic in your space, you want that if you take the neighborhood of 2 sides, the delta neighborhood of 2 sides. So this is the delta neighborhood. Then you want that the third side is contained in these 2 neighborhoods. Okay? And you want this for all the 3 geodesic. So for instance, 3 are 0 geodesic, the F2 is not okay. So okay, I want to introduce the notion of acylindrical hyperbolicity. So I will have a few properties to introduce you before. So, and then I will comment this definition. So if you take an element in your group, you say that G is loxodromic. Okay. For the action on this space, okay, so it's always, I don't repeat it each time, but it's always underlined that it has an action on a space which is fixed. So it is hyperbolic, it's loxodromic, sorry, if the map that goes from Z to X and which send well, if you took you take a point in your space and you iterate it, and you want that this is the quasi-isometry embedding. So in this you have kind of quasi-acts. So for this map is a quasi-isometry embedding for some for some X in X, but then it's equivalent to ask that it's for everyone. And okay, quasi-isometry embedding, it means that okay, if you scale from far away, it looks like the same. So say it otherwise, that it's an isometry up to rescaling by a uniform constant and to do a translation. So in this context, this is equivalent to ask that the distance, between 2 points in the image is less. So there exists uniform constant, A strictly positive, B non-negative, such that this is less than you multiply by A the distance between N and M at the beginning. And you add a constant and you do this thing, minus B. Okay, so if you go far away, the distance looks like this. Okay, and I will. Okay, so this is loxodromic. Another way to say it, it's also that it has two fixed points at infinity, and one is repulsive, one is attractive. Okay, and I will. This is more a notation. So if you take a subset of Y and a constant R non-negative, we will denote by stab R of Y. It will be the element in the group that move any element in Y of at most R. Okay, so this is your element in your group such that the distance between Y and G of Y is at most R for all Y and X. And this will be the R point-wise stabilizer. Okay. And so now, we will arrive to the aggression. So the notion I want to introduce is the notion of the WPD property that Sebastian mentioned before. So an element in your group satisfies the WPD property. Okay. So WPD stands for weak, properly discontinuous. Weak property discontinuous. So an element satisfies the WPD property if if you take 2 points far away, you take some neighborhood, and you want that the number of elements that move these 2 points, these two neighborhoods, are a finite number of elements. Okay, so I will say if for all non-negative and for all X in your space, there exists a constant such that the R point-wise stabilizer of X and H to the power M of X, this is a. So I record this are the elements in your group that move X and H of M, X of at most R. Okay, so you want the elements, so if you take an element, so you take some G, it has to move G here and here and so on here. And you know that elements that satisfy this are finite. Okay, and this is okay. So just so this we don't see it in the definition, but this for the definition, I am assuming that I have an action on a group of hyperbolic space, and so this this stabilizer depends of course about your action. Okay, even if we don't see it. And so this is kind of a definition proposition. So it's proposition because it's not the usual definition of hyperbolicity, but it's one which is equivalent and that I will use for the talk. So a group hyperbolic if it contains WPD elements and it is not virtually cyclic. Okay, so I really implied. So here, I have an action which, here in fact the definition is that if it admits an action on a monotonic space, such that it contains an element that satisfies the property. Yeah.
Is this a weekly element?
Yeah. Yeah. Okay. Okay. And okay. And so in fact this notion of acylindrically hyperbolicity is really is related to the notion of being not simple. Okay. And this for the Cremona group, the question of the simplicity. So okay, the question about the question about the simplicity or not or none of the Cremona group was open for a really long time. It has been asked by Enriquez in 1895. And in fact, the way he asked the question, it looks like that he was believing that it was not, that it was, sorry, a simple group. And in 13, Kanta and Lamy, for algebraically closed field, proves that it was not simple group. And in fact, okay, in my PhD, I found the WPG element in the Cremona group, and using all the machinery of Damani, Girardel, and Ozin, this provides you some normal subgroups. In fact, they say that if you have such an element, then if you take big enough power, the normal subgroup generated by this element to this power is a normal subgroup which is proper of this group. Okay, so the Cremona group is not so, and this it was working over any field. Or any field, and this is that. Okay, and so a remark. Okay, well, and they did. In fact, they use another criterion that they constructed, so a tight element which was not used anymore because WPG is really easier to find. Well, to find, but the article, in fact, it was two kind of part. Let's say one that was doing the same things as Damani, Girardel, and Ozin, and the other one was so it was to find a criterion such that you find some normal subgroup, and then it was to find the element in the Cremona group satisfying this. And what I want to emphasize is that okay, so in the two cases we use really geometry group theory, and in fact, if you want to look at the closed, so you can put also a topology on the Cremona group, and if you look at the closed normal subgroup, then it's a simple group. So in some sense, if you look at algebraic subgroup of the Cremona group, they are not normal. Okay, and so it kind of lets you think that well, the good way to attack this problem was really geometry group theory and not from the algebraic geometry point of view. And for instance, in higher dimension, okay, this group has been proved to be also not a simple group. And they do it really by algebraic geometry method, but they don't recover this case. Okay. So, okay, just to emphasize that this was very important. And okay, the machinery of Damani, Girardel, and Ozin doesn't state just that it's not a simple group, but that in fact it has many normal subgroups. So in fact, it is SQ universal. So meaning that this means that any countable group embeds in a quotient. So if you have a finitely generated group, this means that it has uncountable many non-isomorphic quotients. Okay, and okay, this is not the Cremona group is not, but then you can find well, you can take two WPG elements and then you get the same thing. Okay. And so, okay, and the notion of acylindrically hyperbolicity, this is generally the notion of being hyperbolic, but removing the simple case. So you don't want to be, well, finite, you don't want to be Z, this kind of thing. And for instance, the mapping class group is UTFN is for some n. And so the Cremona group is a group coming from another point of view, but always the question were motivated by the fact that if mapping class group and UTFN satisfied, then we want to believe that it satisfies the things. So this is our way to do a bit. Okay. Okay, so now let's go to, okay, let's define the Cremona group. Well, are there some questions so far? Yeah.
Do you know the Cremona group is hyperbolic or like any proper collection of something?
Yeah, so this is the question that, okay, I think no, but it's not, no, okay. The point that, in fact, if you take some proper, well, some collection of subgroup and you kill them, then you are kind of hyperbolic, but the problem is that they are not proper. So there is this thing of, so, well, at some point I wanted to try to do this, but there were too. Any other questions? Okay, so let's. So for those who wants to know more about the Cremona group, there is a really nice book on construction, on writing by Stéphane Lamy on his webpage. So advertisements if you are interested in. So now the Cremona group. Okay, so definition. So the Cremona group is a group of birational transformation of P2. And I will note it by P2. Okay, and the birational transformation, so they are, okay. Okay, so in general, so I just restrict my case to the surface case. So if you have a birational transformation between surfaces S1 and S2, I want to be projective. So it's an isomorphism between dense open subset. So you find so dense is for the Zariski topology. So up to removing curves, you find the two open U1 and U2, and you want that it's defined an isomorphism. And then so locally, it's given by okay. If it will be isomorphism, it will be locally given by polynomials. And because I ask this to be birational, it's locally given by quotient of polynomials. And why we study this thing is because if you want to classify algebraic geometry, up to isomorphism is really too rigid. And so you get too many classes and it's too complicated to study. So the good notion in this context is to look at birational transformation. Okay, so an example of a birational transformation, so of, and then I will give you, that is not in the Cremona group. So, but will be fundamental for the construction of the hyperbolic space is the notion of blow up. So let P a point in a surface. The blow up of P is a regular map. This means that you can take U1 to be S1. Okay, it's a regular map pi P, which goes from another surface S prime to S, such that, first of all, you want that there exists an exceptional divisor, which is isomorphic to P1. You want that P of P from S prime minus EP to S minus the point P. This is an isomorphism, and that you want to contract EP to P. So what we do is that you have your surface S, and you have an exceptional divisor EP above P, and the map pi P, it contracts EP to the point P, and elsewhere it's an isomorphism. And in fact, what you look at, if you look at the line, so the pencil of line passing through the point P, what you have here is that for any direction of the line, you have a point here. Okay. And So here you have you have to think that here it's not it's not a variety of dimension 3, it's still a surface, but just you have developed your point P and you have splitted the curves. A nice representation is given in the book of Charevich. The first page is nice drawing of what it looks like. And so, because it's an isomorphism between pi p and p, you see that, so elsewhere it's an isomorphism and it contracts this one. So in fact, from here to here, it's well defined, but in the opposite way, it's not defined in the point p. And so locally, this can be written. So you can look at the point. So locally around 0, 0. You can write this in local coordinates. So this belongs to C2 times P1, and you want that xv equals to yu, and this goes to x3. So you see, it's like it is in a variety of dimension 3, but you have an equation. And if you take the good chart, so exercise in a good chart, so meaning that you take u or v equals to 1. This map you can write it locally. You can write pi p from C2 to C2. As A, B, it sends to A. And so this equation just tell you that if you are close to the point 0, 0, you are on some line, and this gives you this coordinate. So the line corresponds to a point on the exceptional divisor. So we'll see in really few minutes that these maps are really, really important for birational transformation. And now I will give you example of elements which are in the Cremona group. So example. No, well, wait. Sorry, I don't. Now, if I take so this is a formal way to say, but then you can look at how it is really. So if you take an element f in dir P2, how does it look like? So f, it goes from P2 to P2. And to x, y, z, you want to associate 3 polynomials. So where the fi are polynomials over k. So here it's way it's sorry. Here it's where the fields place. And to be well defined, you want that they are homogeneous and of the same degree. And you can ask that they have no common factor, non-constant. So this is a rational map, and to be birational, you want that it is an inverse of the same. So birational transformation, well, an element of the Cremona group is the data of 3 polynomials. And so what is called the degree of f is the degree of the phi. And I put here a dash arrow because if x, y, z are 0 of the 3 polynomials, then it's a point which is not well defined. When I put a normal arrow, it means that it's well defined. So, and this is what we call the indeterminacy locus of f. It's the 0 locus of the polynomials, the intersection. Do you have questions so far? So now we'll give examples. So first we can ask about, we are looking at birational transformation, but maybe we want to understand also the automorphism of P2. And so the automorphism of P2, this is a subgroup of the Cremona group. And they are the application of the Cremona group that are exactly of degree 1. And you want it of degree 1 because you want it's an isomorphism, so it has to send the lines to line. And if you say, well, if you take a line here, then you will get here a curve of degree of the degree of the polynomials. Okay. And if you take here F0, F1, F2 homogeneous polynomial of degree 1, and you want that it's inversible, and we are over P2, then this gives you PGL3. Then another example of the Cremona group, this is the standard quadratic involution. Goes from P2 to P2, and to X, Y, Z, it sends YZ, XZ, XY. Okay, so it's quadratic because this is of degree 2. Okay, why it's an involution? So here I present you the projective form, but also before in the presentation, I told you that the birational transformation, it can be given locally by quotient of polynomials, and here we don't really see it happening. So by locally, what I meant is that if I take the chart where Z is not 0, okay, so I replace Z by 1. This is given by F0 XY1 over F2 XY1 and F1 XY1 F2 XY1. And so here we see the form that locally is given by quotients of polynomials. And if we wrote this map in this form, then it's to xy we send 1 over x. 1 over, oh yeah, I'm sorry, I should not have done this. And here we see that it's an involution. Okay, and this map, what does it do? So if you take C2, you add the line at infinity, and you wonder what does sigma. You see that if you take 2 of the 3 coordinates to be 0, then it will be not well defined. So this means that these 3 points are not well defined. And if I take the line z equals to 0, so this is sent to 0, 0, 1. So this will be sent to the point. This will be contracted to the point 0, 0, 1. Okay, and if I do the line y equals to 0, this will be sent to the point 0, 1, 0. And the same with the orange line, it will be contracted to this point. And the inverse does the same thing. So this application is not well defined in the 3 coordinate points, and it contracts the 3 lines. But outside this, it's an isomorphism. Then we have also a monomial embedding. So the one like storic geometry, monomial embedding. So we have in fact a GL2Z inside the Cremona group. And this is given by if you take a matrix A, B, C, D, you can associate the map, which is written in local coordinates as XY is sent to X to the power A, Y to the power B, X to the power C, Y to the power D. In fact, this is also an example of such a map. Okay, and the last subgroup I want to, okay, it contains many subgroups, none, but the last I want to mention is that you can also look at the automorphism of C2, or if you take K to be different of C, of the affine space. And these are the maps that are locally written as XY are sent to P of XY, Q of XY, where P and Q are polynomials. Okay, and if I take if I take a general field here, I can just take a. And even if this is an automorphism group, it's already really huge. And in the exercise of tomorrow, we can see that in fact it contains also some WPG elements. And in fact, you can show that this contains a free product over an uncountable number of generators. So it's quite huge. Okay, and I have okay, just maybe to finish with this presentation. So I wanted to mention another result is that and so we know a generating system for the Cremona group, and this was in fact one of the first theorem about the structure of this group, which was done by Okay, stated by Noether, and it was a gap in the proof corrected by Castelnuovo. So when the field is algebraically closed, the Cremona group is generated by the automorphism of P2, so by PGL3, and the quadratic involution. So we know well the generating system. And you can remark that the generators are all of degree 1 or 2. But still, when you compose, things get wild. Okay, even if the system of generator looks nice, things get wild. And this group is not finitely generated, and even when the field is finite, still this group is never finitely generated. Okay, so and yeah, I will finish with a theorem that said that in fact in the surface case, any birational transformation is composition of this kind of maps. So you can decompose any birational transformation as a composition of blow up of points and contraction of curves. And this is really a powerful tool. So theorem of Zariski. So let F be a birational transformation and S1, S2 surfaces. Okay, regular projective, I want to be in a nice context. Then like this W a surface with the same property, and pi and rho, which goes from S1 to P2 W to S1, and the second one goes from W to S2, that are composition of blow up. So they are you do several times this procedure, so that are composition of blow up. Such that, so we have P, rho, S1, F, S2. This diagram commutes. Okay. So this means that if you look at the groupoid of birational transformation between surfaces, blow up are a generator of this groupoid. Okay. And this is really nice because it tells you that if you blow up some points here, then you get a regular map. And in fact, this is also a composition of blow up. So in fact, we can do just this on the example of the standard quadratic map. So maybe I will. Oh, sorry, I hope I will not destroy it. So I will do on this example how the proof works. So we have our map, okay? And what we want to find is that we want to find the surface here, such that then this one is well defined everywhere. So here we have 3 points where it's not well defined, so we can blow up 1 point. So let's start by blowing up this point. Then we said that the blow up separates the lines who are crossing through the same point. So we have this thing. Up. And then we have the yellow one. And here we have the point E associated to this point here. And here we have this map, the composition of these two. But because it's an isomorphism everywhere, the points were not well defined down, they are still not well defined. Okay, so this here is still not well defined. So we continue and we blow up a second one and then a third one. And then we get something like this. And now everything is well defined. And in fact, to get this map, you have to blow up the points where this one is not, where the inverse is not well defined. Okay. And just a remark, so this will be, well, this is an exercise also for the recitation, is that here I did a nice example where all the points not well defined are down. So we see already in P2. But can happen that for some map that I gave in the exercise, when you blow up a point here, then a new point not well defined appears. Okay, but still the theorem said that in finitely many steps, this ends. Okay, and I want just to add one thing in the last minute I have, is that here you can choose W to be minimal, in the sense that if it exists another W primes that satisfy the same thing with phi prime and rho prime, then you have a morphism that goes from W prime to W, and this means that you have blown up too many points. So this means that here you have blown up points that you have contracted the curves here. So it was useless. And if you do this such a minimal resolution, the last definition I need is that the base point of F, that I will denote by base of F, are the points blown up in the minimal resolution by P, okay? Are the points by pi in the minimal resolution. So tomorrow what I will do is that we will construct the hyperbolic space on which this group acts. We will try to understand a bit its action, and then we'll see how we find WPD element in this group. And thanks.
Okay. Thank you. Any questions? Okay, if not, before thanking Anne again, I remind you we meet at 3 for the next one. Thank you.